Hello and welcome back to Machine Learning. I'm Jivita Christie, and in this video, we are going to talk about how to implement the different evaluation techniques we studied for clustering, which are silhouette width and purity, which we covered in the previous video. So if you want to know what they are, you can watch the previous video. In this video, we will be implementing those. And after that, we will talk about how you can improve the performance of your machine learning model. So let's begin. So let's first start with implementation of the evaluation techniques called silhouette width and purity, which are used to evaluate clustering techniques in machine learning. So to do that, first we will have to implement clustering, and we have already done this program in our previous videos, one of our previous videos on clustering. So this should not be very difficult. I'm just going to go over the program once again. So we have the pandas and NumPy libraries, which we have imported. We are also going to get k-means from sklearn.cluster because that's the type of clustering we are implementing, k-means clustering. To do our measurement of purity, we require the v_measure_score, which is nothing but the purity, which we can get from sklearn.metrics.cluster. Okay, so we are all set with the libraries needed. Now, next, we are going to open our file. So the file that we are going to use is this file with several details about, different kinds of things related to the spine. So there is the pelvic incidence. So these are all medical terms. And based on all these values, you can determine if the spine is abnormal or normal. Okay. So those are the two classes. And you can see over here, pelvic incidence, pelvic tilt, all these values are given. And we are going to separate out the class variables from the target variable. Okay. So what is the, we are going to separate out the predictor variables from the class variables. And all the columns from 0 to 11 are the predictors, can be used as predictors. So we have separated those out using the iloc function, where we specify that we want all the rows, but we want only columns from 0 up to 11. And that's why we mentioned 12, because remember, 12 means it's only going to go up to 11. Next, we remove our target or class variables. So the class variable or the target variable is the final one, which shows whether or not the spine is normal. So that one is going to be our class variable. So we're just going to write this variable over here. And that is the 12th column. The index of that column is 12. So we are going to pass 12 and take that into class variable. Next, we are going to select the features because we don't want to train our model. We don't want to perform clustering with all 11 columns. So I'm going to take 3 columns. You can take more if you want, or you can use all. So I have taken these 3 columns, and specifically in our previous program, when we did clustering, k-means clustering, we took 3 columns because we also wanted to be able to plot it afterwards. So taking 3 columns means you would have a 3-dimensional plot, which was okay, and 4-dimensional plot wouldn't be possible. So we took these 3, okay, pelvic incidence, pelvic radius, and thoracic slope. So these 3 are taken from the data_WOC, which we created here for all 11 columns, rather 12 columns. And then we saved all these values into F1, F2, and F3 features. And we are also creating an array of F1, F2, and F3 using NumPy library.array, and we are using the zip function to create a sort of an array, a 2-dimensional array containing these 3 columns only. Okay, and once though that array is ready, we can apply k-means clustering. And to do that, we have to pass how many clusters we want. So we just want 2 clusters. And the random state, you can specify any number. And then we are storing this model into k-means, and we will try to now fit our values onto it. So we have our feature 1, 2, and 3, which was all stored in x variable. So we are passing that over here and saving our model in model variable. And then we can predict the cluster labels like this. So to predict the labels, we have to use k-means.predict and pass x, which are all the features, and it returns to us all the cluster labels, which you can see here. So these are the labels predicted by our model. Our data doesn't have many rows, so cluster labels are not many. Now to measure the purity, you will be using the v underscore measure underscore score function, where you will pass your cluster labels and you will pass the data class. Okay, so the data class is actual values. Cluster labels are labels predicted by the model. So when you pass both, you can know the purity of your model, which comes to 0.12. If you want to understand what purity is, you can refer the previous video. And the next thing we want is the silhouette score, which we can again get from sklearn.metrics silhouette score. And here in the silhouette score function, we are going to pass x. Remember, we created x by zipping f1, f2, f3 and creating a numpy array. So x is just that. And cluster labels are all these labels predicted. The metric we want to use is the Euclidean distance. I explained in the previous video other kinds of metrics. So if you want, you can take a look at that. You could also take a look at the Python documentation to see what other kind of metric is available with silhouette score. Provide the sample size, which is the length of data. Data is nothing but this pandas array, the CSV file that we read. Okay. Now, since that all the parameters are given, you can just print out the silhouette score, and it comes to 0.40. If you want to understand the significance of purity and silhouette width, you can do that by watching the previous video. Let's now move ahead and talk about how we can improve the performance of our model. One of the effective ways for improving the performance of your machine learning model is hyperparameter tuning. Let's see what that is. So what is that? It is the process of adjusting the model fitting options. And what are model fitting options? For example, if you're working with the k-nearest neighbor algorithm, then a parameter could be the value of k, okay, or the number of nearest neighbors that you want to consider. If you're working with clustering, you could adjust how many clusters you're creating. If you're working with neural networks, you could adjust how many hidden layers you have in your neural network. So all those are examples of parameters, and most machine learning models have at least one parameter that you can tune. The next technique to improve the performance of your model is the ensemble. So what is ensemble? Where you can combine several models together. The models which are combined like this, they are complementary to each other, which means one model would be learning from one type of data set, and it might be working well with that, but there could be some other data set with which that particular model does not perform well. So these models are complementary, which means whatever one model has, the other model doesn't have, and what one model doesn't have is something that another model has. So you could combine the power of all these models together and create one model. Okay. Now this approach is known as the ensemble approach, because ensembling simply means that you're collecting a lot of things together and putting them together. Ensemble helps in averaging out biases of the different underlying models and also helps in reducing the variance. So we've studied bias and variance earlier, so you would understand that. What happens in ensemble? Ensemble methods would combine weaker learners to create stronger ones. So if you combine several weak learners, you might be able to create a stronger one. and a performance boost can be expected, even if the models are just built as usual individually, and then they're just combined together or ensembled together. So here is an example, or rather a diagram depicting how ensemble technique um, works in practice. So what happens here is you have the training data. The training data is separated into different types of training data, 1, 2, 3, 4, and so on. So this could mean that you're either providing the same training data to all the models, or you are using one of those splitting techniques that we talked about earlier in one of the previous videos, and creating different kinds of data sets from the same data set, training data, for different models. Okay. And here you can see there are different kinds of models. So there's naive Bayes, and there is decision tree and SVM, all these models. And then all of these outputs from the models are combined together by a combiner function. We'll talk about that a bit later. And then the final output is generated using all these models together. So that is the ensemble method. So what are the different steps in this process? So first one, build a number of models based on the training data. And for diversifying the models generated, you can take a training data subset, okay, using some kind of an allocation function, or you could use techniques like bootstrapping and stuff like that to generate different data sets. And we have studied bootstrapping earlier, so you know about that. Alternatively, you could use the same training data, but you could use different models. So you could either use models that use the same algorithm over and over, but provide different training data, or you could use different models having different algorithms, but the same training data. So you can make a choice there. And the outputs which are there from all the models, they are combined together using a combination function. And this function can be done in many ways. A very simple strategy would be majority voting. So if suppose you're performing classification and you have 5 models, and 3 out of 5 models are saying that it is a win, and 2 are predicting it will be a loss, then you can go with win because that's the majority vote. Now there are other methods also, like bootstrap aggregating or bagging. This is a very popular ensemble model method to create an ensemble model. So what does that mean? Bootstrapping or bagging is used to generate multiple training data sets, and we have studied this before. So this is very easy to understand now. So you have training data sets, and you have a set of models that are going to learn using the same algorithm. So you have to provide to them unique data sets from the same training data set. And then you can take the outcomes of all the models, you can combine them together using majority voting, or you could just take an average of those outcomes, whatever you like. And so this is a very simple technique, and it also performs very well for unstable learners like decision trees, where even if you make a small change in your data, it will have a big impact on your model. Another method of sort of creating ensemble is boosting. So just like bagging, boosting is also another ensemble-based technique. And in this type of technique, weaker learning models are trained on resampled data, and the outcomes are combined using a weighted voting approach based on the performance of different models. So resampled data, which means you are having one training data, but you are taking several samples from it and providing each sample to a different model for training purposes. And then you will see which of those models is performing well. So based on their performance, you will add a weight to the model. So if some model is performing very well compared to others, then the weight of that model will be higher. So when you take a majority vote, then the voting will be there, the majority will be there, but that particular model which performs, or rather outperforms other models, will have a higher weight, will be given more consideration. The vote of that model will have a higher impact. And there is an algorithm called ADA boosting or adaptive boosting, which is a special variant of the boosting algorithm. And it is based on the idea of generating weak learners and then learning slowly. And the final method is random forest, which is also an ensemble technique. And we have studied this and implemented this as well in our previous videos on supervised learning classification. So what is this? In random forest, we take several decision trees and we combine them to create a forest. So that's why we call it a forest, because it is a combination of decision trees. So each decision tree, you could, like, there are several ways of implementing a decision tree. And so you could have, 4 or 5 decision trees all implemented using different kind of a technique. And then you could take a majority vote, or you could take an average of whatever result they are providing. So if it's classification, you could take a majority vote. If it is, if you're performing regression or something, you could take an average of the result. So that's how you can improve the performance of your machine learning model. And that's it for this video. I'll see you in the next one. Thank you for watching.